In this video, we will see 4 examples of solving non-homogeneous differential equations with constant coefficients. And here we're going to consider high-order problems. For high-order problems, we're going to use the same strategy as for second-order differential equations. Namely, you're going to, first of all, solve the corresponding homogeneous problem, and then you need to find the particular solution. And then you're going to use the superposition principle to combine the first 2 parts. Let's check out the first example. For this example, we just need to provide a form for the particular solution. We don't have to solve this. But we know the form of the particular solution depends on the fundamental solutions. So we still need to do the first step. Namely, we have to solve the homogeneous equation. And we can use the characteristic to solve it. So you're going to change the order of the derivatives into the corresponding degrees of powers, and you keep all the coefficients. So we're going to end with the polynomial equation. This is a cubic equation with 4 terms, and we can try to use, for example, grouping. But unfortunately, the grouping approach is not going to help in this case. And you can try, for example, binomial theory and some other convenient approaches, and none of them is actually helpful. So then we will think about the rational root theorem, or the rational zero theorem. This theorem says, if you have a polynomial of integer coefficients, and if you know this polynomial has a rational zero, here we understand the P and Q, they are relatively prime. Then we know the numerator P is going to be a factor of the constant term, and the denominator Q is going to be a factor of the leading coefficient. So for this particular case, we understand our P, it can be either 1 or 2, because the constant term 2 has only 2 factors, 1 and 2. And the denominator Q, it has to be 1, because the leading coefficient here is 1. So therefore, the possible rational zeros are going to be either positive or negative 1 and positive or negative 2. By the way, these are just some potential rational zeros. Okay, the theorem only gave you some potential ones. It didn't say all of these numbers are going to be roots to this equation. So now, how can we get the root for the equation? Well, we can just plug the numbers into the equation and see whether or not it makes the equation true. Okay, so for example, when we plug the number 1 in, you're going to get 1 minus 3 plus 4 minus 2 is exactly 0. That means we can get r minus 1 as a factor of this polynomial. And the other factor can be obtained from, for example, polynomial division. Okay, so you can just do division of this one by r minus 1. Okay, and pretty easily you can get the other factor is going to be r squared minus 2r plus 2. And now we can get from the first factor, your r is going to be 1. And for the second factor, because it's prime in the real number set, so we use the quadratic formula, we can get some complex roots. And therefore, the corresponding fundamental solutions to the homogeneous problem are going to be, the first one is e to the t. And for the complex roots, you understand the real parts, the real part goes to the exponents, imaginary part goes to the sine and cosine. So we're going to get the 3 fundamental solutions. Now we check the right-hand side of the differential equation, and we just distributed e to the t to this summation, and we can see 3 terms. And among the 3 terms, we notice that the first term is contained in the fundamental solutions. The last term is also contained in the fundamental solutions. And we understand in this case, we have to use actual t's, right? So basically to address the first term, we understand we have to use both sine and cosine. So you're going to get e to the t sine, e to the t cosine. And then once again, because the e to the t cosine and e to the t sine are fundamental solutions, we need to use some extra t here. Okay, so we need these two terms to address the first term. For the second term, because this one is not contained in the fundamental solutions, you simply use sine and cosine. Okay, so you got e to the t times sine 2t and e to the t times cosine 2t. We use these two terms to deal with this. Finally, for the last term, because this guy, once again, is contained in the fundamental solution, so we have to use extra t. So the particular solution has to be in this form. Example 2. So now we have a 6th order differential equation. And we know its right-hand side, but we don't know exactly what are the left-hand side. Okay, the coefficients here, we do not know them. Nevertheless, we know that the characteristic equation of this differential equation has 3 roots here. Okay, square root of 3, 1 minus 2i, and 2i. So for sure, we have these 3 roots. And then the question here is, can we find the particular solution to this problem, although we don't know the coefficients here? Once again, we don't have to solve the problem. We just need to provide a form for the particular solution. Well, this problem looks like incomplete because we understand the characteristic for this problem is going to be a polynomial of degree 6, right? Because the 6th order is going to be 10 to the 6th degree. And then from the fundamental theorem of algebra, we know the characteristic is going to have 6 roots, but now we have only 3 of them. So that's why I said it looks like an incomplete problem. However, if we check the, for example, when you solve quadratic problems, or you use some deeper kind of polynomial theory, then we understand if we have irrational roots or complex roots, we're going to have the irrational number and the complex number always going to come with the conjugate of them. Okay, so that means, for example, in this case, although you have 3 roots given here, but the other 3 roots are actually implied in the given form. Namely, for example, corresponding to the square root of 3, we know there's another root, negative square root of 3, a conjugate to this, okay? And for the 1 plus 2i, you're going to get 1 minus 2i, okay? Sorry, for the 1 minus 2i, you have 1 plus 2i. It's also a root, a conjugate of this, okay? And for the 2i, its conjugate, negative 2i is also going to be a root. So once again, although we have only 3 roots given, but actually from the theories, we already know all the 6 roots. So now you can provide the fundamental solutions. So understand for the 2 irrational numbers, you can just provide e to the corresponding powers, right? And for the complex roots, we have to use sine and cosine, right? The real part goes to the exponent. Imaginary part goes to the sine and cosine. For this one, the real part is 0, so that's why you don't have the e to the, basically it's e to the zeros, right? Okay, so now we just need to use the right-hand side and the fundamental solutions to determine the appropriate form for the particular solution. So here, we just copy the right-hand side and the fundamental solutions. And now you check, you will say the e to the t cosine 2t is contained in the fundamental solutions. So we understand now to address this term, we are going to not only use e to the t times sine 2t. We know once you have a sine or cosine, you have to use both of sine and cosine in your particular solutions, right? So not only you are going to do that, you need to also use an extra t, okay? So we have to do that part for this. And also for this t, we understand for this multiple, we have to use also a polynomial of same degree, right, to address this. So we will say for the t, we use a polynomial of degree 1 to address it. And for the e to the t cosine 2t, because once again, this is part of the fundamental solutions, so you have to use extra t. You have to use both of the sine and cosine parts, and also you have to use extra t, okay? Finally, for the constant, you can simply use a constant to address this. Okay, finally, we're going to do the distribution, and we know the alpha times gamma is still going to be an arbitrary constant, right? The alpha is a constant, gamma is a constant, right? So it's still going to be a constant. So instead of using the product of two constants, we're going to simply write the product as, for example, a capital A. Okay, so you're going to get, so basically you're going to get the capital A here is just alpha times gamma. Okay, and the capital B here is actually alpha times delta. Okay, so and so on. So this will be the particular solution. Example 3. Now we need to solve this differential equation. And once again, we're going to use 3 steps. So step number 1, we solve the corresponding homogeneous equation. And we're going to use a characteristic, which is a degree 4 polynomial, right? But you have only 3 terms. So we know whenever we factor a polynomial, we're going to use a common factor first. And then you're going to say this is just r minus 1 squared, right? So easily we're going to get 2 zeros and 2 1s as roots of the characteristic equation. And then the corresponding fundamental solutions are going to be, we know whenever we have repeated roots, we have to use extra t there, right? So for the first pair, you're going to get e to the 0t, which is just a 1, right? For the second one, you use extra t, you're going to get just a t. And then for the third one, you got e to the t. And the fourth fundamental solution, you're going to get t e to the t. So now we have the fundamental solutions. And when you propose for the particular solution, we have to consider the right-hand side and the fundamental solutions. So now we notice that we have the t here is contained in the fundamental solutions. So we have to use, well, you have to use actually, because you have 1 and the t, both of them there. So you have to use t squared. You have to use 2 extra t's to address this. Okay, so that's why we have the t squared, and then you're going to have, for this t, you're going to use at plus b. Okay, now for the second term, the e to the t, we know is a fundamental solution, and also the t to the t is also a fundamental solution. So to address this term, you have to use another extra t, so that will be a t squared times e to the t. Okay, so finally, we can propose the particular solution in this form. Okay, once again, for the first one, you know, for the t, you're going to use at plus b, right? But because the 1 and the t, they are both in the fundamental solution set, so you have to use 2 extra t's. And for the e to the t, because your e to the t and the t e to the t are fundamental solutions, so you have to use another extra t, right? Yeah, same thing as here. Okay, now we need to determine the ABC, and we need to just plug the y sub p into the original equation to determine the a, b, and c. To do that, we need to find the derivatives up to the fourth order, right? So we'll just carry out the derivatives. The first two terms, very much straightforward because these are powers. The last term is a product. Well, we can just use the product rule. And you can see here, when you do the product rule, you're going to say the first term's derivatives is going to be 2t, right? And then times the second factor. And then you use the first factor times the derivative of the second factor, right? So basically, you can see all the details here, right? We just keep using the product rule for the last term, right? And now, once we find all the derivatives, we can plug them into the equation. This is our equation, right? So we use the fourth derivative, the third derivative, and the second derivative. We simply plug all of them in. And then we just try to carry out the multiplications and combine the like terms. Okay, so you can see here we have quite many different types of functions involved, right? For example, for the e to the t, you're going to have a couple of terms, right? We put them here. For the t to the t, we collect all the t to the t, put it here. And for the t squared e to the t, we're going to collect all of them, put them here, right? And for the t, you're going to have only one term. And for the constants, you can have like two constant terms, right? Put them here, okay? And then we compare this with the right-hand side. So in this case, actually, you can see the last two terms in the left-hand side are canceled out, right? So the 8 plus 4 minus 12 is going to be 0. The 1 plus 1 minus 2 canceled out, right? So you're going to get, the left-hand side will give you 3 terms. Okay, here we also have some cancellation, but you still have some e to the t left. And then you can just compare the two sides. So this is the simplified form. Compare the two sides. Then we know the coefficients, corresponding coefficients, they have to match, right? You have 6at in one side, 1t the other side. So that's why your 6a is equal to 1. And here the constant is negative 12a plus 2b. And the other side, you don't have any constant. So that's why you have a 0. And for the e to the t, you're going to have 2c and 2 in the two sides. So that's why they are equal, right? And this equation system is very easy to solve. So you can get your a is going to be a 6, your b is going to be a 1, and your c is going to be 1 as well. And finally, you get your fundamental solution. Particular solution is going to be, you just plug the ABC into the corresponding form places, right? And then your general solution to the non-homogeneous case is going to be obtained. Example 4. This time, we have an initial value problem. So we understand we have to first of all solve the non-homogeneous problem, and then you have to apply the initial conditions to determine the constants. So first of all, let's solve the equation. And we're going to start with a corresponding homogeneous equation. And we're going to once again use its characteristics. And for this case, because you have r to the fourth and r squared, only these two powers. And also we know r to the fourth is r squared squared, right? So we can just do substitution. We make s equal to r squared. And then we can get, this will be the form. And then you're going to get your s, we know is r squared, right? So you're going to get your r squared plus 1 is equal to 0, right? And you're going to have it twice. So that means your r1, r2, they are going to be, both of them are i's, and r3 and r4, both of them are going to be negative I. So therefore, for the repeated roots, we have to use some extra t's, right? So keep that in mind. So therefore, the fundamental solutions will be, you're going to get cosine t, sine t, because you don't have any real part. The real part is 0 here, right? So e to the 0 is going to be 0. That's why you don't say the exponential. We don't have any exponential factor here, okay? only sine and cosine. And because the roots are repeated, so we have to use extra t's. Now, based on these fundamental solutions and the right-hand side, we can propose the particular solution. Okay, so we notice that the sine t is in the fundamental solutions. And also the t cosine t is also in the fundamental solutions. So we have to just keep using extra t's. Okay, so here we have the situation with no t, 1t, right? But both of them are already included in the fundamental solutions. So therefore, to address these things, we have to just keep using extra t's. Namely, you're going to use t squared and t to the third. And of course, we understand if you have one of the sine and cosine, you still need to use both sine and cosine, right? Now, if you have only one of sine and cosine, you still need to use both sine and cosine, right? So that's why we have the t to the second, t to the third. It's just because the t to the zeros, t to the first, they're already in the fundamental solutions. And you still have the sine and the cosine, right? You still have them. How to handle that? Keep using extra t's. Okay, now we just need to plug this into the original problem and compare the two sides to determine the A, B, C, D. So we just need to carry out the derivatives for this form. Once again, we have some products here, right? So we're going to use a product rule. So as you can see, if I do the derivative for the first factor, so you just use the product rule, right? Derivative for t squared 2t, and then times the second factor, minus t squared times the derivative of the second factor, that's negative sine t, right? For the second one, you do the same thing. Derivative for the first factor times the second, plus the first factor times derivative of the second factor, right? And so on. And then you can just do the product rule again for every term, right? So you can say here, each term will give you two terms, right? So you can, each term will give you two terms, okay? But among these terms, you have some common like terms, okay? And you can combine them, and eventually you're going to get, for each coefficient A, B, C, D, you're going to get three terms involved. But all of them, well, you need to like use the corresponding differentiation rule, in particular product rule again, right, to get the next derivative. Okay, so pretty much we're going to use the same thing here. So I'm not going to like do all the details. So after you take the derivatives, you do the combination of those like terms. Okay, you're going to get your third and fourth derivatives are going to be like this. And now we can plug them into the equation. We need to use the fourth, the second, and the zeroth derivative. Okay, so we simply plug all these things into the equation and give the coefficient 2 there, okay, and then compare the two sides. So that's what we're going to have after we plug the three terms into the equation. And now we can say a lot of like different types of functions, right? We can say a lot of different types of functions. So we simply collect them and combine them. Okay, just to combine the like terms. Okay, now for each function, you're going to just simplify the coefficients. Okay, so you have some combinations, cancellations. So after you combine them, you can get some simplified form. Okay, so for example, the first one comes from the coefficients of cosine. So when you simplify, you get a negative 8a plus 24d, right? And the other side, you have no cosine. So that's why this is equal to 0. And for the second part, you can say here, the a get canceled, right? And the d's, you're going to get negative 24d. But the other side, you have no t times sine t. So that's why you have a 0 here. And then for the next one, you can say the a's get canceled. So you get only 12d. But the other side, you don't have t squared cosine t, right? So that's why you're going to get 0. And for this one, you can say the b parts will give you negative 8b, and then minus 24c. And the other side, you have 8 sine t. So that's why you have 8. And then for the next term, you're going to say the b parts canceled, right? And the c parts, you're going to get a negative 24c. And this is equal to the other side, you have 12 of it. And then for the next one, you can say the b's get canceled, right? And also the c's get canceled. So you have nothing left, all canceled out this term. For the next term, you have the same thing. The c's all canceled out. And for the last term in the left-hand side, same thing, all canceled out. So we only have here a total of 5 equations here, okay? But we know some of them are redundant, okay? So we have 4 unknowns, although we have 5 equations, but we know some of them are not really, you know, for example, these 2 conditions talking about the same thing, right? So easily we can solve this system and get the coefficients. And then we just plug them into the proposed form for the particular solution. And we can get the particular solution. And then you combine this with the fundamental solutions, you can get a general solution. Okay. Now we are ready to apply the initial conditions to determine the constants. But you understand, the initial conditions, many of them are given in the derivatives, right? So we have to find derivatives of this. So once again, we have to use product rule for many terms, okay? So as you can see here, we'll just keep doing the derivatives. If we have to use a product rule, then we just use it. And then you can find up to the 3rd derivative. And now you can just apply the initial conditions, okay? So you can see here, I simply just, you know, put the 0 into the places of the variable t's, okay? So you have, you know, initial condition, when the input is 0, that means you have to replace the t's by 0, right? Okay, yeah, the inputs here, they are all zeros. So you put 0 in. And then the other side, you just use the corresponding values. So for the y and y prime, we got zeros. For the 2nd and 3rd derivatives, you're going to get 1s. Well, it's quite lengthy, right? The equations. But it's not that bad because we have a lot of zeros. For example, sine 0, we know is 0. And we have coefficient 0. So after we, you know, eliminate those zeros, we're going to end with only these many terms. So this is definitely not very bad situation, right? So you can see the first equation, for example, all these terms are zeros, right? You'll have only the first term, c1 times 1 is equal to 0, right? For the second equation, you say this is 0, right? And you have c2 and c3. All the others are going to be zeros, okay? So that's why you have c2 plus c3 is going to be 0, and so on, okay? So if we evaluate the, you know, sine and cosine zeros, you will say the equation system is pretty neat. And for this system, you already got the c1 is 0, right? And then you can easily get your c4 is going to be just 1/2 because c1 is 0, right? c4 is going to be 1/2. And then for the c2, c3, you can use these 2 equations. For example, you can add them to eliminate the c2, and you're going to get negative twice of c3 is equal to 1. So that means your c3 is going to be negative 1/2. And then from this equation, for example, you can see our C2 is going to be the opposite of C3, right? Because the summation is 0. So you can get C2 is 1/2. So eventually, we're going to get the solution to the initial value problem is like this. So here you simply plug the constants into the equation. Okay, that's all for this video, and thank you for watching.